All right, so far we've talked about integrals in a few different ways. The first way we talked about them was using our favorite method of Riemann sum. So a Riemann sum is a sum involving the limit as n approaches infinity from k, starting at n equals 1, for the function, this, I'm just summarizing, it goes nowhere, okay, f of x delta x, right? Then, after we did that, we started to hit geometry. And when we did the geometric, we introduced the actual integral from a to b of f of x dx. And then what we did was we started to talk about this, and we talked about the geometric areas as the shapes and the area above versus the area below. So we would make two shapes and we would sum their areas together, or if one was like this, where you had some space above and a space below, we did the sum of the area above minus the area below. So what we started with was area above minus area below. Then we took that same integral symbol and we found the area under the curve using the calculator. So then we used NINT, or Math 9, as I'll probably refer to it more often. Yesterday, we talked about adding and subtracting integrals together. But one of the things we talked about was what happens if you put a constant a. What does it do? It basically just kind of expands or shrinks your area based on k. So we call k kind of like a constant of integration, and you would have k of b minus a, where k was the new height and then b minus a was your width. So let's expand that today into antiderivatives for definite integrals. So what's it mean to be a definite integral? A closed interval. Good. So a definite integral is on a closed interval. So, or you could say it's fixed. It's a space that is set in time. So we're going to look at antiderivatives today on definite integrals, and we're going to introduce the idea of an antiderivative. Yeah. So an antiderivative for now is going to be the capital letter F, because we're anti-deriving f of x. So we're going to take some function f of x and we're going to anti-derive it so that we get a new function, capital F of x. Now, the c is an arbitrary constant. We're not going to really talk about c for a couple more days, but the most basic definition for the word antiderivative is to take lowercase f of x, anti-derive it, and get uppercase f of x. So we're going to start by finding antiderivatives using the evaluating integrals antiderivative definition. So what that says is if we have our integral a to b of lowercase f of x dx, then this is going to equal capital f of x, where it says evaluating, integrals. Because I couldn't import my PowerPoint, I missed this slide when I was copying and pasting. So this is the evaluating integrals using antiderivatives. And then, as some of you in physics know, we refer to this as capital F of B minus capital F of A. So what you do is you find the antiderivative for the entire function, and then you evaluate that function at upper bound B subtracting lower bound A. So again, you can kind of see area above minus area below. We refer to capital F of x as an antiderivative. And we can say that f prime of x, where this is a capital F of x, would be equal to what? So if we took the derivative of the antiderivative, what would we end up with? Yeah, lowercase f of x. So let's do our power rule in reverse. If you go back to derivatives, if you took the derivative of x to the n, we brought n down in front and subtracted 1 away. To take the power rule in reverse, we're going to add 1 back and then divide by the new exponent. So go back to the first example. First derivative I gave you was x squared. So if I gave you the antiderivative of 2x, that will give us back my x squared, because you add 1 back to the top, so 1 plus 1 is 2, and you divide by that new exponent. So you get x squared. So derivative of x squared is 2x, antiderivative of 2x is x squared. Let's talk about it more specifically at the definite integral that you have on your page. So we already determined that this was 2x squared over 2. We canceled the 2's. What we have to do, because this has bounds, is bring those bounds with us.
That's what you wrote.
Yeah, I did but I did it in general. So now this is out of bound. So what it means is this is the capital, this is like capital F of B, and this is like capital F of A. So what I'm going to do is I'm going to plug capital F of B in, so you get 2 squared, minus, I'm going to plug capital F of A in, so I'm going to do 1 squared. So I get 4 minus 1, which is 3.
Where'd you get the 1? Oh, minus 1. Oh.
Yep, top minus bottom. F of B minus F of A. April 1st.
You told me you wouldn't watch it. I don't have enough.
Okay. Stop. 3x to the 5th. Its antiderivative means add 1. So it's going to become 3x to the 6th. And then when you make 6 your new exponent, that becomes your divisor. So the 1, this is like kind of having an imaginary x to the 0, because x to the 0 is always 1. So then you have to add 1 back to 0, so you get x, and then x divided by 1 is still x. And we're evaluating from 0 to -1. Here's where you have to start watching how you plug in. You plug in the 0 to both pieces of the function first. So you get 3/6, which is 1/2, 0 to the 6th, so that zeroes out, minus 0 over 1, so that zeroes out. But the formula is f of b minus f of a, so you have to subtract all of f of a. So you're subtracting -1 to the 6th. So what do we know about any negative value to a even power? So you get 3/6. What do you know about -1 plugged in for x, and there's already a minus there. So you get minus a minus. So that becomes a positive. So you have 3/6 plus 1, which is 3/2 or 1 1/2. But the negative here tags along. So you get negative 3/2 or negative 1.5. Okay? Sine of x. So we kind of hit on this yesterday. Remember that the antiderivative of the trig functions are the opposite of their trig functions derivatives. So before, all C trig functions had negative derivatives. So now all the non-C starting trig functions will have negative antiderivatives. So what I mean by that is normally when you took the derivative of sine, you got cosine. But when you take the antiderivative of sine, you get negative cosine. And then we're evaluating from pi to negative pi/2. This is why we do so many quizzes with trig functions at values you should know. So negative cosine of pi minus a minus cosine, so it becomes a positive cosine of negative pi/2. Because it was minus a minus. So cosine of pi, again, talking about over. Yep, so it'd be negative a negative 1. So you have positive 1. Plus, now take cosine of negative pi/2. So you're going to go from like 0 and down, or say that it's like 3 pi/2, which is 0. So we get 1. So, example 4, we have 1 to 3 of r over 2 minus 5. You have to make sure when you do these that the variable inside matches the variable of integration outside. And then we apply our rule. So it doesn't matter that the variable changed from x to r, the power rule still works. So r divided by 2. You have to add 1 to your exponent, so you get r squared. Now, it's already being divided by 2, but we have to multiply by an additional 2. So a lot of times when we see that 2 in the denominator, we want to swipe it out because we added a 2 to the exponent. But you have to remember it's not deriving, it's anti-deriving. So it's going to turn your denominator to 4 instead of swiping it out. And then again, we add back an r to the 5. So if you have a constant, its antiderivative will always have a variable added to it. Now we want to evaluate from 3 to 1. So you get 3 squared over 4 minus 5 times 3 minus, there's where you have to be careful. It's minus all of 1 being evaluated. So it's minus 1 squared over 4 minus 5 times 1. So you get 9/4 minus 15 minus 1/4 plus 5. So I didn't combine like terms within there until I actually got all the negatives distributed, because 9/4 minus 1/4 gave me 8/4, which is 2. So 2 minus 15 is negative 13. Negative 13, add back 5 gives you negative 8. So just really trying to work on those skills of doing math without a calculator mentally. So it helps you to see common denominators turn to whole numbers, etc. Come on, 1 over x squared. How can I transform this in a way that I know how to take its antiderivative? All right, so let's bring it up as x to the negative 2. So apply your power rule. Your power rule says add back 1. So you get x to the negative 1. And divide by your new exponent. So you divide by negative 1. And then we're evaluating from 2 to 1. So I'm going to flip those so it's easier to evaluate. So I'm going to put the -1 on top and the x to the -1 on bottom. So I get -1 over x to the 1, evaluating from 2 to 1. So I get -1 over 2 minus a minus 1 over 1. So you get -1/2 plus 1, which is a half. All right. So are we feeling pretty confident about? Are we feeling pretty confident about these problems? The process with which we do them is not very challenging.
So confident.
No. Go ahead and try Go ahead and try number 6 then.
Is that a challenge?
Yes.
All right, you gotta make it x to the -0.
Okay, but 1 over x becomes 0. So it's antiderivative.
1 over x is x to the
When-
-1, so it's x to the
So
-2 over
let's
-2.
let's talk about when we get 0 on a derivative, right? So let's go backwards. Let's talk about functions. Let's start with a quadratic. What's your next derivative? What's its derivative? What's its derivative? Okay, so we talked about the relationship between derivatives and antiderivatives already because we antiderive 2x to get x squared. How could I antiderive 1 over x to get 0? Where's the logic in that? Because you have to have this relationship of antiderivatives and derivatives sharing this. So if I antiderived 0, I'd get back a constant. If I antiderive 1 over x, I'm going to get 0. What did you get?
Both of the answers are -2 over x squared.
No.
Why?
So you said -2 over x squared.
Yes.
That means if I took the derivative of this, right? Because it's the antiderivative. If I took its derivative, I should get 1 over x. So power rule for deriving says -2 times -2, which is +4x subtract 1.
Close.
So that didn't work.
Wait. I don't know.
Remember, you have to antiderive the derivative.
You make that x to the -1. You add a 1. So x is 0.
Right.
1.
But I am telling you then, I want you to think about,
So it's just 1.
I want you to think about other functions. Yeah, I know. I want you to think about other functions we know and about this relationship idea here. If this is what happens with x squared, when else in calc did we have a 1 over x? Or how did we get 1 over x as a derivative? Because he can't actually get it as a derivative either. That's what he was trying to do with his 2x to the -2. What? Remember, if f of x equals ln of x, f prime of x equals 1 over x.
You just have to know the antiderivative of x.
So I set you up for failure with the 1 over x squared. I know.
Thanks for giving me that one. Surprised it wasn't on this.
Oh, well, when you add 1, it magically becomes ln.
But now you will not forget when you see a 1 over x that it is an ln of x.
Right, yeah, 1.
Antiderivative of f prime of x equals 1 over x. So go backwards and you get the natural log of x, don't, from 5 to 1. So again, all we do is plug in. No, you don't even have to do that. I don't want to know. I want you to leave it as ln of 5
Well, I want to know.
minus ln of 1. Really?
Not really.
What's the ln of 1?
Yeah.
Okay. So it's ln of 5.
ln of 5.
Why does it matter?
Because I like to know.
What purpose does knowing this decimal do for you? It doesn't. This is a definite answer.
When there's a letter in there, it's not definite.
Hold on. You writing down a decimal is an approximation. That is not a definite answer. That's the same as saying the square root of 2 equals 1.411.
They told us at the AP thing, don't do that.
Prove that.
Spencer chose to go to the stats lesson for that example.
We killed the one about the ribbon.
That was hard.
Nobody else knew it.
Really? You're welcome.
The guy said, hey man, you're the best one in here. Something
He
like
said,
that.
hey, good work.
I love how Ryan hears what he wants to hear.
Because I back over.
Do you hear that annoying ringing?
Nobody can
He's like,
That's the boiler. That's the boiler. It means that the school's going to either get really, really hot or really, really cold. No, it means that the pressure's unbalanced.
Yeah, I don't think that's gonna happen, bud.
So, shall I trick you again?
No.
Yeah, 'cause
I
I
saw
might-
a color on a window.
I'm gonna do it on the test, so you might as well.
1 over x plus 2. Is this a reverse power rule or an ln? It is.
Yeah, because you have to put those in parentheses.
Good job, Brian.
Plug in your 5, plug in your 1. Ouch.
Not you specifically, just this.
You know, it sucks.
Yeah.
Don't, Spencer. You want to clean it up a little more? What's the natural log rule? What's the natural log rule for subtraction?
You can put it as a power.
No, you can put it as division if you want a single-termed answer. You're not welcome.
We've been recording for 22 minutes.
All right, 0 to 1 of 2x over x squared plus 1. Yes.
What?
Ow.
Okay. Remember,
Split it up into 2x.
remember how antiderivatives work with derivatives. If you had the natural log of u for f of x, what's its derivative? Okay, so let's look at this.
Oh.
1 over u
and u prime.
is 2x. It is.
Oh.
Because this is my u and this is my u prime. So it's ln of x squared plus 1, evaluated from 1 to 0.
You know what? I'm trying. Alright, that first one, it's on 1. The answer.
The ln of 2 minus the ln of 1 is not the ln of 1. Because the rule for subtracting ln's is that it's 2 divided by 1,
My bad.
which is 2. Or you can take into account that the ln of 1 is 0, so you still end up with the ln of 2. So both the subtraction to division work or just knowing ln of 1 is 0 works.
It still makes me upset it's not 10.
I'm going to bet that it probably has to do with Latin. That once we
Sorry,
transformed the
Nostradamus,
words,
you don't know the answer.
Natural log and L.
I am.
Does that not make sense?
All right. How about 2 over x plus 3? So if you try to do the 1 over u and u prime, well, is the derivative of x plus 3 going to give you a 2? No,
Is this a log or something?
no, it's not. Here's where you have to, and this is why like the properties I gave you at the beginning and the properties we talked about yesterday are so crucial to understanding antiderivatives. Remember that if you have a constant of integration, you can pull it out. I can rewrite this so that the top value of 2 gets brought in front of the integration, so that I'm now only integrating from -1 to 5 of 1 over x plus 3. Now, 1 over x plus 3 is a very easy ln, because this is 1 over u is x plus 3. The derivative of x plus 3 is 1, so you get 2, and then inside is your ln of x plus 3, being evaluated from 5 to -1. So I put this in big brackets because you have to take that 2 and kind of tack it along. But when you do your f of b minus f of a, that 2 either has to go to both f of b and f of a, or you have to double it at the very end. So I treat it kind of like as 2. F of b is the ln of 5 plus 3, which is 8, minus the ln of -1 plus 3, which is 2. And again, no, well, the AP test is now we're going to give you an answer for multiple choice that looks like this. I was going to say there are a lot of different ways you can actually go about doing this. You can split this a few ways now. And I want to just review our ln rules with us. If you have 2 ln of 8 minus 2 ln of 2, what's the rule when you have a 2 out in front of your ln's? Bring it up as an exponent. So you could rewrite that as ln of 64 minus ln of 4, and then do your division. So 64 divided by 4. Or here, what? Yeah. Here you could have said, okay, ln of 8 minus ln of 2 is the ln of 8 over 2, which gave the ln of 4, and tagged along your 2 and turned it into an exponent at the end, giving ln of 4 squared, which would also take you back to ln of 16. Okay. Number 10. Is it an ln? Does look like an ln. Why can't it be an ln? I'm missing u prime, right? So it's not an ln. Can I anti-derive this using my power rule? I cannot. Exactly. And you cannot break up a divisor with addition. So I'm dividing by an x squared plus 1. I don't have a rule for that yet. It's a reverse quotient rule, basically, and we don't have a reverse quotient rule. So this is like we have a reverse power rule right now, which means you can break it up into powered functions. That's now is that a continuous function?
Yes.
Are you gonna have a vertical asymptote at all? Because the denominator can never equal 0 because it's an x squared plus 1, so it's a positive plus positive. So it is definitely going to have an antiderivative because it's continuous on the entire function. It's another rule. So what rules did we have that put something squared in our denominators? It is an inverse, right?
Yeah.
Arctan.
Oh.
Okay, so inverse tan x squared plus 1 is 2. So when does the tangent on the unit circle equal 2?
Never.
Of course. It's root 2 over 2 divided by root 2 over 2. No. Or
Why is it 1?
it's the same as 1. What?
I'm sorry, what?
You divide something by itself. I know what you mean.
Because I don't know why we went that.
Divide it by itself.
Stop.
You do it. Why do you miss all that?
Because I was just writing. Remember, it's the inverse tan of x. Because this is the original x. There's no u prime. I just wrote x
I was
squared.
thinking about that, like, that didn't make sense. U prime divided by.
Remember, it's 1 over u squared plus 1 and then times u prime. Well, in this case, u prime is 1, which means u is x. So u has to be x in this case because showing it for Aaron, somebody who can't hear you mumbling.
Every time you do that, you look right at me like I'm.
Because you're the only one who speaks.
I've been speaking this whole
And
time.
I really wish you weren't.
Exactly.
The inverse tan of 1 minus the inverse tan of 0. So inverse tan of 1 occurs at root 2 over 2, root 2 over 2, which is pi fourths. And then the tangent will equal 0 whenever you get 0 divided by 1. So remember, tan is sine over cosine, so 1 is the sine 0 and cosine. Well, I guess pi could work too because you'll 0 out with the negative 1. You're fine, you can do that. This 0 would cancel. I was thinking 0 or 2 pi, but if you do pi, it still works because you're going to get 0 divided by negative 1, which is still 0.
So it would be pi over 2 pi?
In this case, it's going to 0 out no matter what. Because the inverse tan of 0 is at 0. If you picked pi fourths minus pi, you're still going to get, you'd end up with a negative pi fourths. It's 0. It's 0. I was trying to watch it to get to you. I made you a worksheet so you don't have to get the books home. So, take your break now, and I'll give you your homework when you come back.